Let's look at data types. So we've seen that modern computers are digital machines that only work with binary data. So what we need is a binary representation of every data that we want to use in a computer. So the fact that it's impractical to present all data that we need in a computer in a uniform way, and some types of data will be represented with much more bit to correctly represent them than others, computers work with different data types. And we're going to see the most important ones in this unit. So the first one is the Boolean data type. So this is to store whether something is true or false. And its representation is straightforward, as each piece of data will only need one bit, 0 for false and 1 for true. So numbers are codified differently in binary representation. With integer numbers, the codification is quite straightforward, and it actually only depends on the range of numbers you're going to use and if they're signed or unsigned. So to codify the numbers, you only need enough bytes to represent it in binary code, such that you can represent the maximum integers that you will be using. And if you're going to use negative numbers, you just need one more bit to encode it, whether it's a negative or a positive number. So to do so and follow the rules of addition, you can use a technique that is called a 2's complement. So with real numbers, things are getting a little bit more complicated, since with real numbers you can have an infinite number of decimals. So now you need to know how big the numbers are that you want to represent and what is exactly the precision that you want to achieve. How many numbers do you want to have after the decimal comma? So once these parameters are set, you can do a digit by digit binary representation. But if we did so, it would cost a lot of bytes. So instead what we do is, for normal precision numbers, there's a standard 32-bit representation of the floating point number. And this is actually defined in an IEEE standard with number 754, and it defines the representation with 3 components. 1 bit for the sign, positive or negative, 8 bits for the exponent in a base 2 representation, and 23 bits for a mantissa that actually represents the decimal values. So the standard also defines double precision real number codification with 64 bits and also quadruple precision with 128 bits. So another data type we use in computers is text. Text is composed of characters, and characters are chosen from a finite set of different symbols. So to code them in binary, what we can do is we can just apply a translation table that gives a binary code for each character. And these tables exist and they're called character set. A difficulty with this is that there's lots of character sets to choose from, and if we choose the wrong one, we will get the wrong characters, and obviously then we do not have the representation that we want. So the good news is that the most used character sets have the same values for the first 128 characters, which is mostly the letters from the alphabet and the digits. So these are located and mostly the same. So problems usually only appear if we have local characters as accentuated vowels, non-standard Latin numbers or other symbols. So another data type is sound. Sound is stored as a sequence of binary values called sample values. So the time separation between the samples will depend on the maximum frequency of the recorded sound. And as we will have to store more samples for higher frequency sounds. Each sample will have a precision that will depend on the number of bits we want to use to store it. So what we can do after capturing the sound, we can compress it because we can eliminate temporal redundancies. Since, as you can imagine, most natural sounds will have values that are near in a captured file, that values will be similar. And they can be stored with less bits because we can use this similarity. So images is another data type we use in computers. Images are captured with a resolution in pixels. We can see here a lot of pixels on this slide. So images are stored as matrices of m by n values, and for each value is stored as a pixel. And the pixel stores usually the amount of red, the amount of green, and the amount of blue that this precise pixel contains. Since you know that any color can be represented as a combination of red, green, and blue. So depending on the number of bits we use to store each colors, we will be able to represent a different number of colors for each pixel. And this is called the color depth. So again, after capturing an image, it can be compressed because we can eliminate the spatial redundancies, as again there will be zones in the image that will be very similar and that can be stored using less bits. Then finally, there's video data type. Video is captured as a sequence of images. And the images are captured at a rate that is fast enough to be seen by the human eye, and it looks like a moving sequence. So after capturing the video, again it can be compressed to eliminate spatial and temporal redundancies, as again we now will have similar images in similar zones within an image. So we have seen some important data type and their representation in a computer.